orthogonal signal-based signal approximation using orthogonal functions. How the signal is approximated using these orthogonal functions: mean square error, closed or complete set of orthogonal functions, and then orthogonality in complex functions. And we will do some problems related to the above topics. And coming to the second unit, that is Fourier series and Fourier transform. You are already aware of this unit of Fourier series and Fourier transform in your first year course. It includes the Fourier series representation of continuous time periodic signals, properties of Fourier series, Dirichlet's conditions, trigonometric Fourier series and exponential Fourier series, relation between trigonometric and exponential Fourier series, complex Fourier spectrum, deriving Fourier transform from Fourier series, Fourier transform of arbitrary signal, Fourier transform of standard signals, Fourier transform of periodic signals, properties of Fourier transforms, Fourier transforms involving impulse function and signal function, then introduction to Hilbert transform, and finally we'll do the problems related to the above topics. Then coming to the third unit, that is analysis of linear systems. Then here we will discuss about what is a linear system, what is a linear time invariant system, what is a linear time invariant system, etc. This includes the introduction, linear system, impulse response, response of a linear system, linear time invariant system, linear time invariant system, concept of convolution in time domain and frequency domain, graphical representation of convolution, transfer function of a linear time invariant system, some related problems related to linear time invariant systems, then filter characteristics of linear systems, distortionless transmission through a system, signal bandwidth, system bandwidth, ideal low pass filter, ideal high pass filter, and ideal band pass filter characteristics, causality and polylinear criteria for physical realization. Then finally we'll see the relationship between the bandwidth and race time. Then coming to the fourth unit, that is correlation, which includes autocorrelation and cross correlation of functions, properties of correlation functions, energy density spectrum, Parseval's theorem, power density spectrum, relation between convolution and correlation, detection of periodic signals in the presence of noise by correlation, uh, then extraction of signal from noise by filtering. Then it also includes sampling theorem. Sampling theorem includes graphical and analytical proof for band limited signals, impulse sampling, natural and flat top sampling, reconstruction of signal from its samples, effect of undersampling includes aliasing, introduction to bandpass sampling, and some problems related to the correlation and sampling theorem. Then finally last unit consisting of both Laplace transforms as well as jet transforms. Laplace transforms includes the introduction of Laplace transforms, the concept of region of convergence for Laplace transforms, constraints on ROC for various classes of signals, properties of Laplace transforms, inverse Laplace transform, relation between Laplace transform and Fourier transform of a signal, then Laplace transform of certain signals using waveform synthesis. Coming to the jet transforms, it also includes the concept of jet transform of a discrete sequence region of convergence, that is ROC in jet transform, like ROC in Laplace transform, then constraints on ROC for various classes of signals, inverse jet transform, properties of jet transforms, distinction between Laplace transform and jet transform, difference between Laplace transform, Fourier transform, and jet transform. Then coming to the textbooks of signals and systems, so these three are the standard textbooks of the signals and systems. Those are Signals, Systems and Communications by B.P. Lati. Second one is Signals and Systems by A.V. Oppenheim, and third one is Signals and Systems by Simon Haken. And coming to the reference books, here we have two references are there. First one is Principles of Linear Systems and Signals by B.P. Lati, and second one is Signals and Systems by T.K. Rawat. And after completion of this course, the student can able to understand these course outcomes. Those are, first one is differentiate the various classifications of signals and systems, analyze the frequency domain representation of signals using Fourier concepts, classify the systems based on their properties, and determine the response of linear time invariant systems, know the sampling process and various types of sampling techniques, and finally apply Laplacian jet transforms to analyze the systems in both continuous and discrete time signals. These are the course outcomes of our signals and systems. Then coming to the unit 1, coming to the unit 1, that is introduction to signals and systems. So it includes the definition of signals and systems, classification of signals, classification of systems, how the signals are classified and how the systems are classified. Then operations of signals. What are the operations we have to done on these signals? That is time shifting, time sharing, time scaling, amplitude shifting, amplitude scaling, etc. Next, complex exponential and sinusoidal signals, singularity functions and related functions, impulse function, step function, signal function, ramp function. These are the basic functions of the signals. Then similarity or analogy between vectors and signals. Then orthogonal signal space. Then we will approximate the signal using orthogonal functions. Then mean square error, closed or complete set of orthogonal functions. Then orthogonality in complex functions. Then finally we will see some problems related to the above topics. See how the signal is defined. A signal is a function, is nothing but a function of one or more variables that conveys information about some physical phenomena. It is a function of one or more variables that conveys some information about some physical phenomena. Suppose a function f is there. Suppose in the expression f of t1, comma t2, comma t3 up to tn, each of the t suffix k, that is t1, either t1 or t2 or t3 or tn, is called an independent variable, while the function value itself is referred to as a dependent variable. So some examples related to signals, which includes the voltage or current in an electronic circuit. See some voltage. Suppose if you take some voltage, some 5 volts, 10 volts, 15 volts, 20 volts, like that, independent value. Similarly, current value, 2 milliamps, 5 milliamps, 10 milliamps, 6 milliamps, etc. Like that. These are some independent values in electronic circuit. Similarly, the position, velocity, or acceleration of an object. So next one is the force or torque in a mechanical system, a flow rate of a liquid or gas in a chemical process, a digital image or digital video or digital audio. Then the stock market index. These are all some examples of our signals. So finally, signal, how the signal is defined. A signal is a function of one or more variables that conveys information about some physical phenomena. Next, how the signals are classified. How these signals are classified. Here, the signals are classified based on the number of independent variables. Initially, number of independent variables, that is dimensionality. Dimensionality. Number of independent variables means dimensionality. A signal with one independent variable, that is f of x or f of y, like that. A signal with one independent variable is said to be one-dimensional signal. For example, audio signal. Audio signal is one-dimensional signal. A signal with more than one independent variables is said to be multi-dimensional. More than one independent means f of x, y, z, or x, y, z, p, etc. That includes, that is example. If we take the example of a multi-dimensional signal, that is an image. Similarly, continuous or discrete independent variables. Continuous or discrete independent variables. So here a signal with continuous independent variables is said to be continuous time signal. Continuous independent variables. For example, if we take the voltage waveform, continuous independent variables. That is one. Uh, a waveform. Waveform is nothing but continuous voltage waveform. It is a it flows continuously with some voltage. It flows, suppose some 2 voltage, next 5 voltage, next 6, like that. it flows with continuous independent variable value, that is called continuous time signal, that is CT signal. A signal with discrete independent variables is said to be discrete time discrete time signal. Discrete time, there is a difference between continuous time signal and discrete time signal. If you take continuous time signal, it flows continuously, whereas discrete time signal will not flow continuously. The continuous signal can be frozen for some time and it can be divided into equal intervals of time. That is called discrete time signal. Example, stock market index. It is like a discrete time signal. Then continuous or discrete dependent variable. A signal with a continuous dependent variable is said to be continuous value, so that is a voltage waveform. A signal with a discrete dependent variable is said to be discrete valued signal, that is a digital image. So a digital image consisting of a number of pixels. So these are located at various locations. So like f of x, y, z, or f of x, y, or f of x, etc. Next, a continuous valued CT signal is said to be analog signal, and discrete valued DT signal is said to be digital signal. Analog signal example is voltage waveform, and digital signal example is digital audio signal. So these are all the classifications of the signals. Then we will see the graphical representations of these signals. The continuous time signal is like this, and the discrete time signal is like this. It is continuously flowing from minus infinity to plus infinity. It is continuous signal, whereas it is represented by x of t. Whereas coming to the discrete time signal, it is not continuous. This continuous time signal is frozen for some time, and it can be divided into equal intervals of the time. These are all the equal intervals, like this discrete time signal is represented. Next, coming to the what is the need of studying signals and systems? What is the need of studying signals and systems? So here, engineers build systems that processes or manipulate signals. What is system? A system is something which takes a signal as the input signal, it processes something and it will give some other signal as the output signal. So system can take signals as the input and it will give signals as the output. Next, we need a formal mathematical framework for the study of such systems. Such a framework is necessary in order to ensure that a system will meet the required specifications. Example for home and safety. If a system fails to meet the required specifications or fails to work together, negative consequences usually ensue. When a system fails to operate as expected, the consequences can sometimes be catastrophic. Then coming to the signals, already we discussed about the continuous time signals and discrete time signals. Continuous time signals can flow continuously. Discrete time signals are nothing but the continuous time signals can be frozen for some time and it can be divided into equal intervals of time. Here, the continuous time signal is called a function, whereas discrete time signal is called a sequence. Continuous time signal is called a function and discrete time signal is called a sequence. Although strictly speaking, a sequence is a special case of a function where the domain of the function is the integers. We will use the term function exclusively to mean a function that is not a sequence. Then nth element of a sequence x is denoted as either x of n or xn, x suffix n. Here it is represented as x of n or x suffix n. Then coming to the properties of signals. What are the properties of signals? Here, first one is even signal. How the signal is said to be even signal? As we already know about the even numbers and odd numbers, etc. Now we are going to see the even signals, odd signals. What is meant by even signal? Suppose if you take x of t is the signal, if x of t is said to be even signal, it is equivalent to x of minus t. What is x of minus t? X of minus t is nothing but it is the mirror image of the original signal x of t. See, it is defined like this. A function x of x is said to be even if it satisfies a x of t is equal to x of minus t for all values of t. Similarly, a sequence x of x is said to be odd if it satisfies x of n is equal to x of n is equal to x of minus n for all values of n. It is also here x of t is nothing but it is a signal. X of n is nothing but a sequence. Sequence is nothing but it is a discrete time signal. X of t is nothing but a continuous time signal. So geometrically, the graph of an even signal is symmetric about the origin, whereas uh, if we take some examples of even signals, here the x of t is represented like this, x of n is represented like this. Suppose x of t from 0 to t, it is represented like this. Its mirror image is nothing but x of minus t. These two are equal. If these two are equal, then this function x is said to be even function. Coming to the discrete time signal, x of n is represented from 0 to n like this. And this is nothing but minus infinite to 0. It is the mirror image of the x of n. So this x of n and x of minus n both are equal. Then this x of n entire function is called even signal. So like this, even signals for say signal and sequence. Signal and function and sequence is represented like this. And coming to the odd signals, how the signal is said to be odd signal if the function x of t is equal to minus of x of minus t. That is nothing but the, the original signal is equivalent to the its mirror image, and it can be reverted inverse inverse one inverse one. This is nothing but inverse one. It is the inverted mirror image of the original signal. Suppose a function x is said to be odd if it satisfies x of t equal to minus of x of minus t for all values of t. Similarly, a sequence x is said to be odd if it satisfies x of n is equal to minus of x of minus n for all values of n. Geometrically, the graph of an odd signal is antisymmetric about the origin, whereas the graph of an even signal is symmetric about the origin. See, an odd signal x must be such that x of 0 equal to 0. Here, these are the examples of function and sequence. Here, x of t is represented from 0 to t like this, and x of minus t is this one, but it is inverted. It is nothing but x of t is equal to the inverted mirror image of x of t. These two are equal. Similarly, x of n and x of minus n, which is inverted like this, reverted. So this is x of n from 0 to n x of n. This is x of minus n, which is inverted. So x of n is equal to minus of x of minus n for all values of n. So these two are the examples of odd signals. Then coming to the periodic signals, how to how the periodic signal is defined. What is meant by periodic signal? Suppose a signal sinusoidal signal is there. Sinusoidal signal is repeated with a particular time period until infinity. Then this is called periodic signal. So mathematically it is represented as x of t is equal to x of t plus t for all values of t. So a function x is said to be periodic with a period t or t periodic if for some strictly positive real constant capital T, the following condition holds, that is x of t is equal to x of t plus t for all values of t. Next, a periodic function x is said to have frequency 1 by t. F equal to, it is nothing but the reciprocal of the time period, that is 1 by t. And angular frequency which is represented by omega, omega equal to 2 pi f. Here f is 1 by t, so omega is 2 pi by t. A sequence x is said to be periodic with period n or n periodic if for some strictly positive integer constant n, the following condition holds, that is x of n equal to x of n plus capital N for all values of n. An n-periodic sequence x is said to have frequency 1 by n, then angular frequency omega is equal to 2 pi f, that is 2 pi by n. A function or sequence that is not periodic is said to be aperiodic. So there is no gap between A and periodic. Aperiodic means non-periodic function. Okay, or a function or sequence. Sequence is also aperiodic. So you see some examples of the periodic signals. These are some examples of the periodic sequence. So it is a signal and it is a sequence. That's why it is a sequence is nothing but a series of signals. Series of signals. Signal is represented by x of t. So it is the signal with the time period this one. With this particular time period, it will be repeated until infinity. And here also it is the sequence with the period this one. With this sequence, it will be repeated until infinity. So but it is varying from minus infinity to infinity. That's why it is called sequence. Next, coming to the deterministic and random signals. These are all the basic basic signals. So deterministic signal means it is predictable. It is predictable. So the behavior of the signals is predictable with respect to time. There is no uncertainty with respect to its value at any time. Mathematically, we can express these deterministic signals like x of t is equal to sine 3t. It is deterministic signal. Then coming to the random signals, there is no predictability in random signals. So the behavior of these signals is random, that is not predictable with respect to time. Similarly, there is an uncertainty with respect to its value at any time. These signals can't express mathematically. For example, if we take thermal noise generated, this non-deterministic signal, thermal noise can be generated. It is randomly generated. That's why it is the example for random signals. Next, continuous time signals uh, and systems. Here we will discuss about the independent and dependent variable transformations. Then, as we already see in our syllabus, operations on signals. So here we have to do the operations time shifting, time scaling, amplitude shifting, amplitude scaling, etc. So what is meant by time shifting? Time can be shifted either by right side or left side by so and so units. So time shifting means a time translation. So here the signal can be translated towards the right side or left side. So time shifting is also called as translation, maps the input signal x to the output signal y as given by y of t is equal to x of t minus b. So it means that here where b is a real number, it means that the original signal x of t can be shifted by b units towards right side or left side. Here y of t equal to x of t minus b is represented by here the signal original signal can be represented towards right side by B units. Such a transformation shifts the signal to the left or right along the time axis. If B is greater than 0, Y is shifted to the right by B relative to X, that is delayed in time. Similarly, if B is less than 0, Y is shifted to the left by B relative to X, that is advanced in time. So here, based on the real number, it can be shifted to either right side or left side. So this is called time translation or time shifting. See some examples of the time shifting or time translation. See, these are the examples for the time shifting or time translation. See, suppose if we take x of t minus 1, x of t minus 1 and x of t plus 1. So x of t, suppose x of t is like this is x of t, suppose x of t is this one, then x of t minus 1 can be shifted to 1 unit like this. These two are same. And x of t plus 1 can be shifted by 1 unit towards the left side, minus 1. So these are the examples of the time shifting or time translation. Then time reversal. Time reversal means time reflection. It is the mirror image of the original signal x of t, x of minus t. X of t is the original signal and x of minus t is the mirror image of x of t. So time reversal, it is also known as a reflection, maps the input signal x to the output signal y as given by y of t is equal to x of minus t. That is, x of t is represented by x of minus t. That is nothing but a mirror image of x of t. Diametrically, the output signal y is a reflection of the input signal x about the vertical line t equal to 0. So it is represented like this. So this one is x of t. X of t signal is the exact. If you take the mirror, if you put the mirror at here, it will reflect like this. So x of minus t. So x of minus t is nothing but the mirror image of x of t. Next, coming to the time compression or expansion. It is also called as dilation, time compression or expansion. Suppose x of t is there. X of t can be compressed or it can be expanded. The time compression or expansion, it is also called as dilation, maps the input signal to the output signal y as given by y of t equal to x of a t, where a is a strictly positive real number. Such transformation is associated with a compression or expansion along the time axis. If a is greater than 1, y is compressed along the horizontal axis by a factor of a relative to x. Similarly, if a is less than 1, y is expanded or stretched, that is stretched, expanded means stretched, along the horizontal axis by a factor of 1 by a relative to x. If y of t is said to be y of t is equal to x of a t, then it is compressed signal, and y is equal to x of 1 by a, then it is expanded signal. See some examples of the compression and expansion of our signals or dilation of signals like this. See x of t is the original signal. This is the original signal. Then this is time compression. It can be compressed. It is represented by x of 2t, and x of t by 2 is time expanded. It can be expanded. Okay, these are the examples of time expansion or compression, or this is also called as dilation. Next, coming to the time scaling or time stretching. The time scaling maps the input signal x to the output signal y as given by y of t equal to x of a t, where a is a non-zero real number. Such a transformation is associated with a dilation, that is, compression or expansion along the time axis, and or and or time reversal. If a is greater than 1, the signal is compressed along the time axis by a factor of mod a. If a is less than 1, the signal is expanded, that is stretched, along the time axis by a factor of mod 1 by a. If a equal to 1, the signal is neither expanded nor compressed. If a is less than 0, the signal is also time reversal. Dilation means time expansion or compression, and time reversal commute. The time reversal is a special case of time scaling with a equal to -1, and time compression or expansion is a special case of time scaling with a is greater than 0. So time reversal is special case of time scaling, and time compression or time expansion, that is dilation, is a special case of time scaling with a is greater than 0, and earlier one is a equal to -1. See, these are some examples of time compression, time scaling, time dilation, etc. This is the original signal x of t. X of t. This is the original signal x of t. X of minus t is like this. So this is the mirror image of the original signal x of t, and this is x of 2t is time compression, compressed signal, and this is stretched. X of t by 2 is time expanded signal. Next, combined time scaling and time shifting. Consider a transformation that maps the input signal x to the output signal y is given by y of t is equal to x of at minus b. X of at is compressed signal, that is time scaling, and minus b, t minus b is time shifting. That's why it is represented as y of t is equal to x of at minus b, where a and b are real numbers, and if a is not equal to 0, it is a is not equal to 0, real number. These two are real numbers. The above transformation can be shown to be the combination of a time scaling operation and time shifting operation. Since time scaling and time shifting do not commute, we must be particularly careful about the order in which these transformations are applied. The above transformation has two distinct but equal interpretations. First, time shifting x by b, and then time scaling the result by a. First, the time scaling x by a, and then time shifting result by b by a. Note that the time shift is not by the same amount in both cases. See, See, x of t is given like this. Here it is represented both time shifting and time scaling operations. Here initially we'll see time shift by 1 and then time scale by 2. So time shift by 1 is the original signal can be shifted towards right side by 1 unit like this, and it can be scaled by 2 p. Let us take p of 2t equal to x of 2t minus 1. So it can be represented like this. Then time scale by 2 and then time shift by 1 by 2. So time scale by 2 is it can be compressed like this, and then time shift by 1 by 2, that is q of t minus 1 by 2, it is equal to x of 2t minus 1 by 2, or it is equal to x of 2t minus 1. So finally it is represented like this. X of 2t minus 1 is represented like this. And coming to the amplitude shifting. So so far we discussed about the time shifting, time scaling, time time reflection, and combination of time shifting and time scaling, etc. Okay, next coming to the amplitude shifting and amplitude scaling. The next class we will discuss about the remaining topics. Thank you.